I would like to welcome you to section 2. In section 2, we're going to go through IPv4 addressing, and you will learn how to design, implement, and deal with different aspects of IPv4 addressing. Are you ready? Let's get started. We're going to start this section by introducing IPv4 structure, and you will understand how this 32-bit address organized. This is IPv4 header, and as you remember, it is added to our packet in encapsulation process, and it is removed from the packet in the encapsulation process. Let's have a quick review on the fields. Version field shows the IP version, and obviously for IPv4 it is 4. Length shows the header length, because we may have some optional fields that may make the header length a variable value. DS field or differentiated services field is used inside QoS or quality of service, which prioritize the packets for processing. Packet length shows the packet length, obviously. The next three fields are involved in segmentation. Identification, flags, and fragment offset shows how a TCP segment or UDP segment divided into different IPv4 packets. TTL or time to live is a very important field. If we have loop inside our routing infrastructure, this will help us to prevent a packet to loop around the network indefinitely. How? It's very simple. TTL has a value, let's say 255 or 256. Whenever a packet goes through a router, this field decremented by 1. And whenever a packet received by a router that has the TTL value of 0, that router will drop that packet. The protocol field shows the upper layer protocol. For example, for TCP, it is 6. Header checksum is very helpful also. It will help us to understand if we have received the packet correctly. And finally, the two most important fields for CCNA routing and switching are source IP address and destination IP address. And as you can see, they are 32-bit fields. So each IPv4 address could be a 32-bit one. Each IPv4 packet is just like an envelope. It has a source address and it has a destination address, where it comes from and where it goes to. As I mentioned in the previous slide, each IPv4 address is a 32-bit address. The way we show IPv4 addresses is called dotted decimal notation, or DDN. As you can see, we have 4 different parts, each part separated by a dot. If we change this notation to a binary version, you can see each part has 8 bits. So we can call it an octet or a byte. And therefore, each octet or byte can have a value of 0 to 255. Although there are lots of restrictions, and we will talk about them later. It is important to understand that IP address is the unique identifier of hosts inside TCP/IP networks, either IPv4 or IPv6. Each IPv4 address divides into 2 logical parts. The first part is called network ID, and obviously it is common between all hosts that reside inside a specific network. That makes sense. It's a network ID, so it should be common between a network hosts. And the second part is called a host ID, and it should be unique for each host. So these 2 logical parts create a unique identifier or a unique IP address for a host. Question may arise now. How we can understand which part of our IP address is network ID and which part is host ID? The question's answer is subnet mask. Subnet mask is a 32-bit address that determines which part of your IP address belongs to network ID and which part belongs to host ID. How? It's very simple. Let's say this is our IP address in binary format. Subnet mask could be an address like this one. As you can see, there is no signs of non-consecutive ones and zeros. For example, you cannot have 010 or you cannot have 101. Subnet mask starts from left with ones, and after ones, the rest will be the zeros. Or it could be all ones or all zeros as well. But you cannot have non-consecutive zeros and ones. And the ones determine the network ID. So they are masking your network. Wherever you have one inside the subnet mask, the relative part inside the IP address would belong to network ID. And the zeros determine the host part or host ID part. One of the design considerations for IP addresses is the number of hosts per network, because we need to design enough IP addresses per network so each host could have a separate unique IP address. Based on the information from the previous slides, we know how to determine this. It comes from this formula, 2 powered by n minus 2, in which n is the number of zeros in subnet mask, or in other words, n is the number of host ID bits. For example, if we have 8 bits inside our host ID part, we can generate 256 IP addresses minus 2. What is this minus 2? There are 2 specific IP addresses per network that we can't use them. The first one is the IP address with all zeros in host ID, because this is reserved for pointing to the network address. And we use this network address in routing. We will talk about routing in next sections. The next IP address is the IP address with all ones in host ID. And this is the broadcast address for that network. I will talk about the broadcast in next slide. In IPv4, we can have 3 types of messages, and in relation, we have 3 types of addresses. The first type is called unicast. Unicast messages are going from one host to another host, and we use unicast addresses for this purpose. The next one is multicast messages. Multicast messages are going from one host to multiple hosts, and we used multicast addresses for this sending. And finally, broadcast messages. Broadcast messages are going from one host to all hosts. Which all hosts? The all hosts that are reside in the same broadcast domain. Do you remember the previous slide? I told you you cannot use the broadcast address as the IP address of a host. This is why. If we need to send a broadcast inside the network, we use that address. There are also some other reserved broadcast addresses as well. IPv4 has 5 classes. In the early days of TCP/IP, we were bound to use these classes and their default subnet masks. But after introducing CIDR, which I will talk about it later in next videos, we were free to use the desired mask. This is the first octet that determines the class of your IP address, and you can see the different ranges. Class D, which starts with 224 to 239, is for multicast addresses. I told you in the previous slide. If you want to send multicast messages, you can use one of these addresses. Class E is experimental class, and you can't use them in an operational network. Something is missing in this table. What is that? Exactly, 127. 127 addresses are reserved for loopback adapters. Loopback adapters are kind of networks inside network adapters. And 127001 is the address that has been reserved for all network adapters around the world. And we can use this IP address for troubleshooting. What type of troubleshooting? I will talk about it later in routing section. And as the final topic to conclude today's video, IPv4 can be assigned in 2 different ways. The first way is called manual or static, in which network administrator assigns IP addresses manually to hosts. It is good for small networks, but in medium to large networks, it's not possible to do this process manually. So we need someone to do this process automatically for us. And we engaged DHCP server to dynamically assign IP addresses.